Chapter 2.6, Rational Functions and Their Graphs. So in this chapter, we're going to be looking at all the polynomials that we've gone through so far, all of the facts about them, and applying them to a new type of function, a bit more complex than just a simple polynomial, but with a lot of the similar properties. So what we're going to be doing is dividing polynomials. But instead of just doing the division, we're going to see what the graphs of those divided polynomials actually look like. So, in order to do that, we're going to start by defining a thing called arrow notation. So we've seen a bit of arrow notation when I introduced end behavior in chapter 2.3. Now we're going to look at it a bit more formally. So here we have f of x equals 1 over x, one of our common functions that we should generally know what it looks like by now. So the left branch curve of 1 over x approaches the x-axis, or in other words, y equals 0, as x goes toward negative infinity. So we can see where I have it circled that as I head along the x-axis, right here, the graph of the function heads towards 0, because 1 over 10, 1 over 100, 1 over 1,000, these are all getting smaller and smaller. Right? Even though these are negative numbers over here, so negative 1 over 10, negative 1 over 100, negative 1 over 1,000, it's still going to get smaller and smaller and smaller, but never actually hit 0 or cross it. Similarly, as the graph approaches x equals 0 from the left, the curve sort of drops down, and on the right, it veers upward, right? And this is because as the absolute value of x gets smaller, so x is going toward 1/10, 1/100th, 1/1000th, well, 1 over x is going to get much, much larger, infinitely larger. But again, x will never be 0 because we can't divide by 0. And finally, the right branch curve approaches the x-axis as well. It just approaches it from the top instead of the bottom, but we can still see that as I head along my x-axis, the x values are getting larger and larger, but the y values, the output values, 1 over 100, 1 over 1,000, 1 over 1,000,000, they're getting smaller and smaller and smaller, but never crossing 0. Okay, so what can we do with that information? We can use arrow notation to show that x, or f of x, is approaching a particular value. So it's a way of simplifying all of these statements. So here we have the basics of arrow notation. So x arrow, a with a little minus sign up in the, sort of like, it's a superscript minus sign, so kind of up where you would put an exponent. That means x is approaching a from the left. So x is less than a, but getting really close to a. Plus sign up in that corner is x is approaching a from the right. So x is greater than a, but getting really, really close to it. X arrow infinity means x is approaching infinity. In other words, we're going along the x-axis and we just keep going off to infinity. X arrow negative infinity is the same thing, but now we're going off towards the left side of the x-axis. And similarly, f of x approaching infinity or negative infinity means f of x, our y value is going up, our y value is going down, and f of x approaching a means our output is approaching a particular value. So let's look at our statements. The left branch curve approaches the x-axis as x goes to negative infinity. In other words, we could simplify that using x heading towards negative infinity, because we're on the left, x is going to negative infinity, and f of x is approaching a in this case is some value 0 for us, that y value 0. So we can write this as x approaches negative infinity, or as x arrow negative infinity, f of x arrow 0. As x approaches negative infinity, f of x approaches 0. Then as the graph approaches x equals 0 from the left, the curve drops, but as we approach from the right, the curve rises. So, as x approaches 0 from the left, so that's 0 with the minus sign, f of x is dropping, so f of x is heading towards negative infinity. And as x approaches 0 from the right, so with the plus sign, f of x is rising. So f of x is going towards positive infinity, which we write like so. The right branch curve approaches the x-axis as x goes to positive infinity. So x arrow positive infinity, f of x arrow 0. Like so. So this is a simpler way of noting the behavior of our graph at certain values or as we go off towards infinity if there's a particular pattern. So you'll notice that, well, for 1 over x, which is an example of a rational function, which is what we're going to be studying, we get these special properties where our function tends to approach values or approach infinity and stuff like that. This leads us to a new definition called an asymptote. So first, a vertical asymptote, which we will often abbreviate to VA of a graph, is a vertical line, x equal to a, where f of x tends towards positive or negative infinity as the input approaches a on at least one side. Note the at least. So here, again, I have my 1 over x. I could draw this little dashed line at x equals 0, and we know that this graph is never going to cross over this line, and we know that the graph heads towards positive infinity on one side, negative infinity on the other, without crossing. So in other words, a vertical asymptote occurs as x approaches a minus or a plus, so a from the left or a from the right. F of x approaches positive infinity or negative infinity. Doesn't matter which, and yes, there are examples, as I have up here at the top of the screen, where we only need it to happen on one side for it to be considered a vertical asymptote. So, for most of our cases in this with rational functions, it's going to end up having some infinity, some approaching infinity on both sides of our asymptote. Because that's kind of how rational functions work. But eventually we'll see examples where it's not quite like that. Just not in this chapter. Now, also note that a graph can have infinitely many of these vertical asymptotes. It's not limited to only one. So we'll see in this class only usually like 2 max for what we're going to be working with, but it can have as many as we want. And in fact, there are examples that literally have infinite vertical asymptotes. You'll see that more in Pre-Calc 2 if you head on to there when you start learning about some trigonometric functions. Now the flip side of that is called the horizontal asymptote, or abbreviated to HA. And this occurs at the line y equals b, where f of x approaches the line as the input increases or decreases without bound. So remember this word without bound. Anytime you see without bound, we're talking about going towards infinity. So if we are taking x towards positive infinity or towards negative infinity, what is happening? Is there some pattern? In the past with our polynomials, we said, okay, as x goes towards positive infinity, maybe f of x goes towards positive infinity as well, right? We'd be going off this way. Or maybe this way, or this way, or this way, right? As x went towards an infinity, positive or negative, f of x went up or down, but it went off to infinity. Now when we work with rational functions, quite often we'll get this pattern where instead of our function heading off towards infinity, it'll sort of approach a value. So, in this case, for 1 over x, we have our graph approaching the line y equals 0. So f of x goes towards 0. And this happens on both sides, whether we're going towards positive infinity or negative infinity. Now, it doesn't have to happen the same way on both sides. A graph can have a maximum of 2 horizontal asymptotes. One for what's happening towards positive infinity, one for what's happening towards negative infinity. Sometimes it'll have only one, sometimes it'll have none, but it'll never have more than 2. With our rational functions, we're most of the time just going to end up with one, But once we get into the next chapter, there will be situations where things are a little bit different than that. So, what is a rational function, though? A rational function is a function that can be written as the quotient of two polynomial functions, p of x and q of x, where we state the domain to be anytime q of x does not equal 0. So, the general form of a rational function is p of x over q of x, where we write each of these in polynomial form. So ap x to the p plus ap minus 1x to the p minus 1 plus down to a1x plus a0 over bq x to the q plus bq minus 1 x to the q minus 1 plus all the way down to b1x plus b0. Our typical polynomial definitions here. So here are some examples and non-examples. So 1 over x squared, that's one of our common functions, which is a rational function. 3x plus 2 over x squared minus 1, that's a polynomial over a polynomial. 9x cubed minus 19x squared plus 2x over x. Notice that, yes, this x could be canceled out here, and we'll talk about exactly how to do that because common errors in doing that cancellation. Doesn't matter. It's still a rational function. Because 3x plus 1, that's also a rational function. There's a secret divided by 1 right there that we can take note of, and so we'd say q of x equals 1. 1 is technically a polynomial. However, things that are not polynomials are basically, or that are not rational functions, are basically anything that isn't a polynomial over a polynomial. So 2 to the x power, that has x in the exponent. That's an exponential function, which we'll be learning about a lot in the next unit, but it's not a rational function. Log of x over x, again, that's next unit stuff. Definitely not a rational function, even though there is an x. There is division. It's not a rational function. The absolute value of x minus 1, or even the absolute value of x minus 1 over x, doesn't matter. Absolute value breaks it from being a rational function. Square root of x plus 2 over x, not a rational function. Square root can't be part of a polynomial. So remember, polynomials are just simple x to a power times a number, a bunch of terms added together. That's all you can really do. Those powers having to be positive and whole numbers. And so, rational function can only be that polynomial over polynomial, and that is it. If anything else is happening, it's not a rational function. We don't know how to work with it yet. Alright, so now that we know what our rational functions look like, let's talk about some facts about some of these rational functions. So, the domain of a rational function is all real numbers excluding those that make q of x equal to 0, right? So, for our first example, 1 over x squared, q of x is x squared, so we can't have x equal to 0. That one's a pretty simple one. For our second one, we want to take q of x is x squared minus 1, so x squared minus 1 can't equal 0, so x squared can't equal 0. So x, we square root both sides. X cannot equal, x squared cannot equal 1. That's my bad. So x cannot equal positive or negative 1. Remember that positive or negative, that's important. 9x cubed minus 19x squared plus 2x over x. Doesn't matter that I could factor this out in some way. All I care about is how it's presented to me. X cannot equal 0. And here, well, my q of x is again 1, so there's no problems in the domain. So we say the domain is all real numbers. Now notice that I did factor this function now. I factored this one. This can help me find those points where I end up dividing by 0, right? So I could solve the equation like I did, with a slight error, but we could solve the equation like I did. Or we can factor it and see a little bit easier that there should be a 1 and a negative 1 taken out of there. Alright. Now, vertical asymptotes, they're going to occur every time x equals a, where q of a equals 0, but p of a does not equal 0. So, in other words, if the factor does not cancel, we get a vertical asymptote. So, factors don't cancel here, we're getting a vertical asymptote at x equals 0. Factors don't cancel here, so we're getting 2 vertical asymptotes for both of these x values. But this x, it is going to cancel. So in fact, we don't get a vertical asymptote. And this one, well, once again, there's no problems in our division because there is no obvious division. So we don't have any vertical asymptotes. However, if our factor, x minus a, does completely cancel, we get a removable discontinuity or hole in the graph at the point a, g of a, where g of x is the simplified form of f of x. So in other words, this function right here can be simplified where I will cancel out these x's. So my g of x would be 9x minus 1 times x minus 2. Okay, that's the simplified form, but I still have to keep the same domain. So I still have to note that there's this point that's just going to be missing. There's this hole in the graph. There's this removable discontinuity. It's this little piece that makes the graph not continuous, but I can kind of just remove a point to show that. That point being what happens when I plug in 0. So when I plug in 0 to this function, I'm going to get 0 minus 1 is -1, 0 minus 2 is -2, -1 times -2 is +2. So I in fact get a hole at the point 0, 2. So here we have vertical asymptote at x equals 0, x equals plus or minus 1, a hole at 0, 2, and neither for our final function. Now, can you have holes and vertical asymptotes? Absolutely. If there had been just another thing here, like x plus 3, I would have gotten a vertical asymptote at -3. That's fine. As well as the hole. You could have multiple holes, multiple vertical asymptotes. There's no rules about that. Now, what about our horizontal asymptotes? These are a little bit trickier because there's something you have to kind of memorize about them. So we get these 3 cases. It's all about the degree of our numerator versus the degree of our denominator. So, if the degree of the denominator is greater than the degree of the numerator, so for example, here I have x squared is the highest powered term of my denominator, so degree 2, and 4x is the highest powered term of my numerator, so degree 1, so numerator less than denominator. Then the horizontal asymptote is at y equals 0. So in this case, it's just as simple as that, horizontal asymptote at y equals 0. This is because my denominator sort of dwarfs my numerator to such an extent that, just like 1 over x, we end up getting these really large numbers on the bottom while the top is still small. So we get closer and closer to 0, just like 1 over x did. Now, if the degree of the denominator equals the degree of the numerator, so here I have numerator 3x squared, denominator x squared, and remember, degree comes from not the first term, but the term with the highest power. So term with the highest power is x squared for both of them, so they're equal. Then the horizontal asymptote will occur at y equals an over bn, or in other words, the coefficient of the leading terms. So the coefficient of the leading term on the numerator is 3. Coefficient of the leading term in the denominator is technically 1, even though we can't see it. So our horizontal asymptote occurs at y equals 3 over 1, or y equals 3. And finally, if the degree of the denominator is less than the degree of the numerator, so here we have 3x squared versus just x, we don't get a horizontal asymptote at all. But there's a possibility of what is called a slant asymptote. So in this case, no horizontal asymptote, but let's investigate it further to see, well, what is a slant asymptote? The graph of a rational function has a slant asymptote, if the degree of the numerator is exactly 1 more than the degree of the denominator. So to find a slant asymptote, we do our polynomial division. The quotient of that division is the equation of the asymptote. So here, the degree of the numerator is 2, the degree of the denominator is 1, so it's exactly 1 more, which means we do have a slant asymptote. So we have to go through the division. So we can, in this case, we could actually use synthetic division if we want to. I'm going to go through the long division instead, just for thoroughness, since that works in all cases. So let's see. Let's build this out. 3x squared minus 2x plus 1 divided by x minus 1. So we're multiplying x by 3x to get 3x squared minus 3x, and we subtract that all off. Cancel. So remember, distribute, so that'll become a plus. 3x minus 2x is x plus 1. Then x to get to x is going to be another 1. That'll be x minus 1. We're subtracting it off. Cancel. Distribute, so that becomes plus. So this will be a positive 2 in the end. But note that, once again, I said the quotient is the asymptote. So the quotient is the 3x plus 1. I don't care about the remainder here. I didn't need to even find what the remainder was because it didn't matter. All that matters is my slant asymptote, just like it shows in the graph on the side, is at y equals 3x plus 1. So notice what a slant asymptote really looks like is this diagonal line at the linear function y equals 3x plus 1. And then our graph will sort of follow those the lines that are given. So we had a vertical asymptote at x equals 1, which we can see because if I plugged in 1, I'd get division by 0. And so my function sort of looks like it's weirdly pointy on either side, but it's still passing the vertical line test. Be very careful about that. So we can see it passes the vertical line test, but it's sort of like housed within these sort of triangles, so it looks a little bit different than a lot of other functions. Well, that's a little bit of a weird case, but in general, how do I figure out all these facts about my functions? Let's look at a very common type of question you could be asked. So find the following information for f of x equals x squared minus 1 over x squared minus 2x minus 3. So how do I do this? Essentially, my first step is always going to be factor. Every single time, you're going to need to factor it. So we're going to factor this. X squared minus 1 is going to factor using a difference of 2 squares to x plus 1, x minus 1. X squared minus 2x minus 3 will end up being x plus 1, x minus 3, like so. Then, well, we can note that those x plus 1s do cancel, but we have to remember how that cancellation is going to affect our function in general. That cancellation still has to be noted within our domain. That's going to cause a hole. So let's go through and find all of the information that we need. So our y-intercept is going to occur when I plug 0 into the function. So I can plug 0 into the version where I have the canceled out stuff because it should work out the same way. So 0 minus 1 is, we're going to get, so 0 minus 1 over 0 minus 3 is going to equal negative 1 over negative 3, so 1/3. We get this y-intercept at 0, 1/3. X-intercepts are going to occur when I plug, when I set the numerator equal to 0. So numerator equal to 0, we're going to get the point 1. So we'll have an x-intercept at 1, 0. Vertical asymptotes are going to occur whenever the denominator equals 0. So denom equals 0, but remember the cancellation, so that x plus 1 doesn't give us a vertical asymptote. So denominator equals 0, comma, numerator not equal to 0. So in this case, we'll get a vertical asymptote at x equal to 3. Notice that I give my intercepts as points, because they are specific points, whereas asymptotes should always be noted as lines. It is the line x equals 3, not a point at 3, a line. So if you just tell me that the vertical asymptote is 3, that doesn't give me any information. X equals 3, that gives me the information that we're looking at a whole line. So, you will be marked wrong if you just state 3, or if you state it as a point, because that's very wrong. It has to be stated x equals 3, and for horizontal asymptotes, y equals whatever it will be when we get there. So our holes, once again, remember we have that cancellation. Hole is going to occur when I plug -1, because it would have been a -1, into the simplified form of the function. So that will give me -1 minus 1 over -1 minus 3, which is -2 over -4, or in other words, 1/2. So a hole will occur at the point -1, 1/2. So holes are points, just like y-intercepts and x-intercepts. Horizontal asymptote, that's a line. So the horizontal asymptote, we can see the degree of the numerator and denominator, they're the same. So when the degree is the same, I get an asymptote at the ratio of the coefficients of the leading terms. The coefficients are 1 and 1, so in this case, we get y equals 1 over 1, which is 1. And if I have a horizontal asymptote, I don't get a slant asymptote. There's none. And so that's all of our information that we can get from this. Now, how does that translate into a graph? We're going to be getting to that momentarily, but let's just sort of look at it for the moment. So here we can see this removable discontinuity at -1, 1/2. We can see the x-intercepts at 1, 0. We can see the y-intercept, which I didn't mark off, but the y-intercept is at 0, 1/3. We can see I've put dashed lines for our asymptotes. You should always include dashed lines for your asymptotes. And we can just kind of see that our graph follows these asymptotes. So having all of this information is generally almost enough to give us an idea of what the graph should look like. There is one more fact that can help, though. So the multiplicity of our zeros and our asymptotes can give us some information. So we already know what multiplicity of zeros tells us. It works the same way for rational functions as it did for polynomials. But for vertical asymptotes, odd multiplicity, which our x minus 3 has, means that the arrows on either side of the vertical asymptote will approach different infinities. Whereas even multiplicity, say it was x minus 3 squared, would mean they would approach the same infinity. In other words, it would look something more like this. So odd multiplicity, one goes negative, one goes positive. Doesn't necessarily tell us which side, because it could go like this. It's still going to be up to you to find enough information to figure out which way is it going, but, well, I already knew I had a point here, and a point here, and a discontinuity here. So I can draw my line, follow my asymptotes, and then knowing that I should be approaching a different infinity, getting something shaped approximately like this is a logical next step. So that's the kind of thought process you should have as we build our functions. But for now, let's look back at our basic reciprocal functions and remember all of the facts we know about them. So, the plain 1 over x reciprocal function is an odd function. F of negative x equals negative f of x. It has origin symmetry. It has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Notice that x equals 0 has odd multiplicity here. So we're approaching two different infinities. Now, for 1 over x squared, our reciprocal squared function, It's even, so f of negative x equals f of x. It has y-axis symmetry. Still has the same vertical asymptote and horizontal asymptote, but there's different behavior around it because x squared means that the vertical asymptote at 0 has even multiplicity because it's being squared. So we approach the same infinity on either side. So how can we use our knowledge of these basic reciprocal functions to graph certain types of other reciprocal functions? Essentially, we can use our knowledge from chapter 1, where we learned how to work with transformations. So we're going to apply those transformations to a reciprocal graph. So here we have g of x equals 1 over x plus 2 minus 1, and we want to apply transformations to f of x equals 1 over x in order to attain final graph of this. So we can see this is indeed a rational function, but it's not presented in the same way as other rational functions because I could bring this up into my numerator by finding the common denominator, etc. But remember, we can use polynomial division to sort of write our functions like this, right? If I go all the way back for just a moment to here, we can see, notice how I took a reciprocal function, a rational function, and simplified it, in quotes, whether you consider this simpler or not is dependent on the example, but we've rewritten it in a different way, where I now have this stuff going on, and then a smaller rational function. So we can do stuff like that too, and this is sometimes helpful in our graphing. Not always, but it's something we can do. So in this case, you really only do it in this, in the way we're about to do, if it's already presented in this way. So 1 over x plus 2 minus 1. We're going to begin with our graph of 1 over x, identifying the asymptotes and a few points and all of that. So here's our basic 1 over x graph. Again, something we should be fairly familiar with. Now we look at g of x and we identify our transformations. So first, we look at our x plus 2. And so remember, this is inside of f of x, right? This is f of x plus 2 would equal 1 over x plus 2. Inside means horizontal transformations. So, horizontal transformation, essentially, remember, f of x minus c means shift by c. Specifically, we're going to shift left or right, depending on the whether we have a positive or a negative number. So, if it is x minus 2, we would go to the right. X plus 2, we'd go to the left. So in this case, this is x plus 2. We're shifting to the left by 2. Then our minus 1, well, that's outside. That's f of x minus 1 would equal 1 over x minus 1. So it's outside of our reciprocal. So we shift down. So we've done our left shift, and now our downward shift. And so this is what our final graph would look like. Which is a pretty simple thing to do if we're given something where there's not a heck of a lot going on. But most of the time you're going to be working with rational functions that are a lot more involved. So let's look at one like that. So here I have x squared minus x minus 6 over x cubed minus 3x minus 2. A lot more going on here. Can't really see obvious relations to 1 over x or 1 over x squared. Maybe I could do some division to help, but not really because this is x squared over x cubed, so it's not going to come out so nicely. So what am I going to do instead? Well, first, just like before, I am always going to start by factoring my function, both top and bottom. Okay, so once I do that, I'm going to end up with x plus 2 times x minus 3 over x plus 1 squared times x minus 2. All right, so I've got that. What can I do with that? Well, I need to find my intercepts. Basically, we're going to go through all that information I showed that we can find before. But now we're going to really get into how to use it. So, my intercepts are going to occur at, again, my y-intercept is what happens when I plug in 0. So when I plug in 0, 0, 0, 0, I'm going to get 2 times negative 3 is negative 6 over 1 squared is 1 times negative 2 is negative 2. So that's going to be 3. So I'll get a y-intercept at 0, 3. And then my x-intercepts are just setting the numerator equal to 0. So when is the numerator 0? That's going to be negative 2 and positive 3. So like so. I get these 3 intercepts. Okay. Next, I want to note the multiplicity of those x-intercepts, though. Y-intercept, we don't care about that. But the multiplicity of those x-intercepts is going to be helpful. So x plus 2 occurs once, x minus 3 occurs once, so the multiplicities are both 1. That's pretty simple. We know that odd multiplicity means we're going to cross. So we're just going to make a note of that so that we can make sure that that actually happens as we're graphing. Okay, next we go for our asymptotes and holes if there are any. So we can pretty quickly see there are no holes in this one because there's no factors in common top to bottom. For the vertical asymptotes, I'm setting the denominator equal to 0. So I'll get a vertical asymptote at negative 1 and a vertical asymptote at 2. Specifically, the multiplicities are going to be 2 for that negative 1 and 1 for that positive 2. Like so. So I put them in and I make a note. Multiplicity even means they approach the same infinity. Multiplicity odd means they approach different infinities. Next, my horizontal asymptote or slant asymptote, depending on what's going to happen. So my horizontal asymptote, well, it's actually a little bit easier to think about the horizontal asymptote in terms of the original function. So I'm just going to sort of pop us back here for a second. Now that we can see the original function, we can definitely see the degree of the numerator versus denominator, right? So degree 2, degree 3. Denominator has higher degree. When the denominator has a higher degree, the horizontal asymptote is always at y equals 0. So we have a pretty easy horizontal asymptote here. Don't have to do any extra work. It's just y equals 0. And because we have a horizontal asymptote, there won't be a slant asymptote, so we can stop there. Notice that I have placed all these dashed lines on the graph. Make sure you're doing that. Don't just assume you know how to work without these dashed lines. Put the dashed lines. You won't get full credit without your dashed lines. All right. So next, what we're going to do for thoroughness is find some points between and beyond known values. So this is a step that I know everyone loves to skip. And in fact, I generally could get an idea of what the graph should look like based off of the information we already have. But one reason that you should always do this is because sometimes things are a little bit trickier than you expect. Second reason is because you're not always right. And so plugging in a few values is a good way to get an idea of what things should look like. Reason number 3 is if you forget how to find any of the previous information, simply plugging in points can help you realize what that information should be anyway. So it'll help you figure out if you were wrong. It'll also help you figure out how to find the answers if you don't even know how. So on the labs and tests, etc., if you don't remember how to do something, just start plugging in points. It's really going to be very helpful in your graphing. Okay, so I plugged in a whole bunch of points. Notice a few things here. Our last step is going to be to sketch, and we need to make sure to follow asymptotes and not to add extra intercepts. This is a big one. Don't add extra intercepts. Pay attention. If we just had function like this, you might be tempted to follow the asymptote by doing something like that. But would you look at that? I just added an extra intercept, right? That's bad. Don't want to do that. So, adding those extra points is a good way to remind yourself not to do that, because we can see, oh, well, if I'm going to follow my asymptote, well, I can do this instead, right? Maybe I wasn't quite sure whether I came to this from the bottom or from the top, though. Well, I have to have come from the top, otherwise, again, I would have an extra intercept. So I have to have come from the top. I have to do something like this in order for me not to cross the x-axis more than I need to. Okay, so I follow my intercepts. Following intercepts means we're adding these arrows. We're going off towards infinity, right? So make sure you're doing that it should approach it but not look like it's heading off to cross it. Crossing it is bad. Don't do that. But that's for vertical asymptotes. Crossing vertical asymptotes is bad. Crossing horizontal asymptotes actually does happen sometimes, and in fact, in this case, it is going to happen. But maybe not exactly like you expect. So notice that, again, if I didn't have all those extra points, I have a point on my asymptote, right? And so maybe I've figured out, oh, okay, I have to do something like this. I haven't given myself any more information, but I know I can't cross, I can't add an intercept here, so I have to have done something like that in order for this to work. And then I remember, okay, approach same infinity. So this is going like this. This one, different infinity, so it's coming like from here. But then I come down to here, and then a lot of people are going to want to just go whoop like that. Because I crossed. So then what? How am I supposed to follow this infinity? Do I just go straight from here? Well, no, not exactly. Essentially what's going to happen, now, again, we have our points back. Essentially what's going to happen, I'm going to come down, I'm going to not make this weird little bump. Let's try that again. I'm going to come down, I'm going to cross, I'm going to go like this. And maybe I need to add more points to really know, but we always need to follow our infinity. So I go down below it, and then I just sort of come back up. So there's this turning point, like so. And similarly, coming from here, I come up, I cross here, I keep going up, I get to this point, and then I come back down, and then I'm sort of following it. Again, I'm allowed to cross my horizontal asymptote, and in fact, you technically can cross it multiple times. You could cross it infinitely many times. It's entirely possible to have a graph that sort of does like this, as long as it's getting closer and closer as we head towards infinity. That's not really the type of graph we're going to be looking at in this class, but it's something you might see later when you start working with trig functions in Pre-Calc 2, etc. So in this case, we just need to remember that even though we cross our asymptote, we come back to it so that as we head towards infinity, we are still approaching it. Now it looks like I've just drawn a straight line on it. It's hard to really show that I am getting just very, very close without actually crossing. So in actuality, this is what it should look like in the end. And now notice, we have successfully crossed both of our x-intercepts like we were supposed to. We have successfully approached the same infinity for one asymptote, different infinities for the other asymptote. All of these points make sense, and we're done. So this is the optimal way that we can graph a rational function, is add those extra points, because sometimes there are going to be parts that are a little confusing, that aren't entirely obvious what you need to do in that area, especially when you are crossing an asymptote like that. How do you approach it? Which side do you come from? If you just plot some points, that's how you can find out. Yes, knowing these facts is very helpful, but it's still better to check your work by plugging in a few numbers. So plug in -3, plug in -1.5, and see what do you get. Do you get a positive number or a negative number? You don't even really need the explicit value. You just need to know, are you going to be above or below the axis? Something like that. So please, don't be lazy about it. Plug in numbers. Alright, So next we're going to look at how do I write a rational function if I were given the graph to start from. So if you're given that a rational function has x-intercepts at x equals x1, x2 through xn, and vertical asymptotes at v1, v2 through vm, and none of these match, so there's no holes, then the function can be written as a times x minus x1 to a power, x minus x2 to a power, and so on, over x minus v1 to a power, x minus v2 to a power, and so on. This is the general form of the factored rational function. All of those powers are going to be determined by the behavior of the graph at corresponding intercepts or asymptotes. And that stretch factor a, that's what we call this a because it's all about that vertical stretching, that can be determined, just use some point on the graph. Any point, often the y-intercept is going to be your easiest point. As long as it's not an x-intercept, just plug something in to solve for a. So here we have an example of a graph. This one, in fact, has a slant asymptote, but we're going to ignore that for the moment. Just kind of hope that that slant asymptote makes sense when we're done. So I've given us a few points. I've given us our vertical asymptotes. We should be able to figure out probably what this function is. So we start from the basic rational function factored, and we're going to look at those x-intercepts first. So those x-intercepts occur at -3 and +1. So I put those in my numerator, x minus 1, x plus 3. And they're both to a power. But what power are they? That's going to be based on the behavior around them. We crossed straight through -3, and we bounced off of +1. Bouncing means even multiplicity, so we're going to put 2 for that power. Crossing straight through, odd multiplicity, specifically 1, because it's not all wiggly, right? So we get x minus 1 squared, x plus 3. Next, we're going to look at the vertical asymptotes. The vertical asymptotes occur at x equals 0 and x equals 2. So I'm just going to put those into my denominator. So x minus 0, x minus 2. Now normally, x minus 0 I would just write as x, so I'm going to simplify it to that in a moment, but realize that that's what x minus 0 is, or that's when we just have just x. It's the same thing as saying x minus 0 in parentheses. So, what are the multiplicities of those asymptotes? Well, we're approaching two different infinities, right? So, multiplicity 1, different infinities, multiplicity 1. Yes, it could be multiplicity 3 or multiplicity 5 or whatever odd number you want, but we're just going to go with lowest degree here because that's all we can really assume. Then our final step is to figure out this a value. Don't forget the a value. The a value is important, though in this case it's going to come out pretty easily. You still need to remember and check for it. So we're going to take sum point, the sum point being the one that I've highlighted here, so 3, 8. We're going to plug it in. So we get 8 equals a times 3 minus 1 squared times 3 plus 3 over 3 times 3 minus 2, which is 24 over 3. 24 divided by 3 is in fact 8, so 8 equals a times 8, so a would be 1. So yes, this comes out nicely with a being 1, but that is not always the case. Please don't forget your a. Make sure to check whether it's 1 or something else. So in the end, this function would be x minus 1 squared times x plus 3 over x times x minus 2. And if we really wanted to be thorough, we would check our work by seeing, does the very clear asymptote, slant asymptote that's present actually match what would happen if I did the division here? It should. We're not going to go through that right here, but it's something that you would want to think about. Ways to check your work. Is this asymptote accurate? So the final thing we're going to look at for this chapter is just a couple of application type problems. So a very common application we'll see is averages. So a software company manufactures virtual reality headsets. Suppose the company has a fixed monthly cost of $600,000 and it will cost $50 to produce each headset. We're going to answer the following questions. So first, we want to write the cost function C of producing X headsets. So our cost function should just be something we understood how to do back in chapter 1, where we have this fixed cost, and we add a multiple of our variable cost. So our variable cost is $50, so $50 per headset, X headsets, so that's 50X. And then we add in the fixed cost of $600,000. Right? So that one is a nice linear function, something we've worked with before. What we haven't worked with yet is, how do I find the average cost function? Average cost is often denoted as C with a bar over top of it. So remember that an average means we divide by the number of things that we're adding up, right? Well, the number of things we're adding up is the number of headsets, which is, in fact, X in this case. So we will just simply divide by X number of headsets. So our average cost is $600,000 plus 50X all over X. And that's generally how your average functions are going to work in problems like this. Now, if I'm going to find any particular value, all I have to do is plug them in. So I'm not going to go through the plugging in step, but I will talk about the interpretation of these. So I plug in 1,000, 10,000, 100,000, I get 650, 110, and 56. Again, you should really check on your calculator to make sure you know how to do that, because that is something that you will have to be able to do on your own. So check that you're getting the right answers. Parentheses matter. But what do these mean? Well, the 650, it's $650, okay, per headset. That's the unit of this average, is dollars per headset. Dollars per headset. Because we're asking what is the average price. Average price is $650 per headset if we've sold 1,000 of them. $110 per headset if we've sold 10,000 of them. $56 per headset if we've sold 100,000 of them. That's how averages work. Think about the units. Units on the bottom are headsets, and the units on the top are dollars. Dollars per headset. So that's where that's going to come from. It wouldn't make sense for me to just say the average cost is $650. It wouldn't make sense for me to say it was 650 headsets. You might think it makes sense to say the average cost is $650, but we still need that extra little bit of information which says $650 for what? $650 for a headset. Well, how is this working exactly? It's going down, right? This average price is going down. Why is that? Well, we're sort of approaching a particular value, and that's what that last question is getting at. We went from 650 down to 110 down to 56. What's going to happen in the long run if the company keeps producing more and more headsets? If it goes from 100,000 to 1,000,000 to 1,000,000,000 to 1,000,000,000,000 headsets, which is a lot, obviously, but let's say they could do that. What would happen in the long run? Well, that long run is really just talking about the horizontal asymptote. What happens if we took X towards infinity? If we made infinitely many headsets, what would happen? We would have to look at the horizontal asymptote. And in this case, our degree, X over X, they're the same degree. So we look at the ratio of coefficients. Coefficients are 50 and 1. So in fact, our horizontal asymptote occurs at y equals 50. So with more and more headsets, the average cost will approach $50, and that's something you can check by plugging in larger and larger numbers. That we should never cross $50, but we should just keep getting closer and closer to it. So just a special note here is, anytime you see the phrase long run, you should think what's happening as X goes towards positive infinity. Which, in this case, means where is the horizontal asymptote? Now let's look at one last example involving area. So the figure shows a page with 1-inch margins at the top and the bottom, and half-inch side margins. A publishing company is willing to vary the page dimensions subject to the condition that the printed area of the page is 50 square inches no matter what. So we want to express the total area of the page A as a function of the width of the rectangle containing the print X. So in other words, we're going to call X this width right here, and Y will be the height of the printed area. So if I want to look at the printed area, well, printed area is then just X times Y, that rectangle. So then, well, what do I do with that X times Y printed area? How is that going to end up relating to my total area? If there's still an X and Y in there, my total area involves the rest of the page. Well, just like I did with our previous rectangle exercises, I'm going to want to solve for one of my variables. So I end up getting the printed area is xy equals 50, because it has to be 50 square inches. So instead of it being a perimeter equal to something, it's now an area equal to something. And then y would equal 50 divided by x. So I'm still doing the same thing as I did in those perimeter versus area problems from chapter 1.10. But now I end up with a rational function for my y value. So what do I do with that? Well, let's look at the total area. So the total area is going to be the area of the entire rectangle. So that's x plus half inch, so x plus 1, and y plus 1, 1, so y plus 2, to make that full rectangle. Once I substitute in my y for the y in that equation, I do end up with an area function with all x values, like I wanted. But, well, there's this little rational function in the middle of the multiplication going on. Actually, I can make this entirely look like a normal rational function, like so. Well, how did I get there? I made this 2x over x, so this is 50 plus 2x over x. And then I multiplied in that x plus 1 to get here. So it is a rational function, which is why we're introducing it in this chapter. So what happens when I ask, what is the domain? Well, remember, we're working a real-world problem. So yes, I know I can't divide by 0, but in fact, I can't have any length less than 0. So we're starting from 0, and we're going positively. But is there anything that's going to stop us? That's the question. So before, we were limited by the fact that x had to be greater than 0 and y had to be greater than 0 when we worked with those perimeter problems, right? Well, now that's still true. Y has to be greater than 0. But, well, let's look at this. 50 over x has to be greater than 0. Well, if 50 over x is greater than 0, and when would it ever become less? It's only going to be less if x is negative, right? Which we already know it's not. So x can go off towards positive infinity, and we're never going to cross 0, right? Because 50 over x is just like taking our rational function, our normal reciprocal function, and yeah, it's times 50, but that's not going to change the fact that it has this horizontal asymptote at y equals 0. So in fact, we're never going to cross 0. So my domain ends up being 0 to infinity. X can be infinitely long. It would look pretty ridiculous for a piece of paper to be infinitely long, but technically I can do that. So what would the area be in the long run if x were stretched out infinitely, though? Well, remember long run? Long run means horizontal asymptote. What's happening as x goes towards infinity? Okay, well, there's 2 x's up here. This is going to end up being degree 2, but I'm going to multiply it out just to be sure. So this is actually equal to 2x squared plus 50x plus 2x, so 52x plus 50 over x. Well, that's degree 2 over degree 1. So higher degree in the numerator, I'm not going to put us all the way back on this one, but remember, higher degree in the numerator means possible slant asymptote, but definitely no horizontal asymptote. So what would that mean? Well, no horizontal asymptote means we're not approaching a particular value. And in fact, if we went through the process of finding the slant asymptote, we'd see this is just going to go off towards positive infinity. Infinitely. So the area can be infinite as well. Which is a little bit weird to think about, but, well, if I had x as really, really long, or really, really wide, I guess, and y as really, really thin, I can keep stretching this out. It's technically possible to get this infinite area. So, with that, we've seen rational functions. We've seen polynomials. We're finished this unit. So, hopefully, guys can figure out how all of that stuff that we've learned about polynomials over the last several chapters are going to relate to our rational functions and how we can use that to sort of expand our knowledge. And really the only things we've added here are this concept of asymptotes. So, but making sure that you're plugging in and checking your work, check, plug in. I swear it'll save your grade, at least. So please do that. And then we're going to move on to exponential functions next.